Welcome you all to another video of our electromagnetic theory chapter. In last video we discussed about del operator, how del operator is used to calculate gradient, to divergence, to curve. I have also given you some numericals. I think you must have done all the numericals, and if you face any problem, let me know in the comment section so that I can clear all your doubts. So here we will discuss about basic laws. What are the basic laws we are going to use in electromagnetic theory? Mainly the laws of electrostatic and magnetism, or magnetostatic you can say, are used here as the basic laws or fundamental laws of electromagnetic theory. Because from the name you can see electromagnetic, electrostatic and magnetostatic both combined are there. So the basic laws are, one is in electrostatic, that is Gauss law in electrostatic, and Gauss law in magnetism. So what is Gauss law in electrostatic? Gauss law in electrostatic states that the net electric flux, the electric flux is the dot product of electric field and area vector. The net electric flux through any closed surface of any shape, any random surface you can take, but it should be closed, in an electric field is equal to 1 by epsilon naught times the net charge enclosed by it. So net electric flux equal to Q by epsilon naught, or flux you can directly write down integration closed surface over S E dot ds, because electric field intensity is E, area vector is ds, small area you can take, which is equal to Q by epsilon naught. This is Gauss law in electrostatic. This is the first law we had discussed. So it states that net electric flux is equal to Q by epsilon naught. Always remember, any type of flux, whether it is electric flux, magnetic flux, any type of flux if you are going to calculate, its mathematical formula is dot product of given field, whether it is electric field, magnetic field, and area vector. So dot product of electric field and area vector is said to be flux. Since we are calculating the electric flux, it is dot product of electric field and area, E dot ds, which is equal to 1 by epsilon naught times the total charge enclosed by it. So which is equal to Q by epsilon naught. Clear about the first? Second one is Gauss law in magnetostatic or magnetism. It states that the net magnetic flux through any closed surface of any shape in a magnetic field is always zero. Then why zero? Because you must have remembered one theorem or one concept that magnetic field always form closed loop. The number of magnetic line choppers entering the surface must be equal to the number of line choppers leaving the surface. So the total change in flux is always zero here. So magnetic flux over any closed surface enclosing a particular volume is always zero. That means you can write down B dot ds integration over S is zero. This is the second theorem. One is Gauss law in electrostatic, another one is Gauss law in magnetism. Then another two theorems are, one is Faraday's laws of electromagnetic induction, another one is Ampere's circuital law. So Faraday's laws of electromagnetic induction states that whenever the magnetic flux linked with the coil changes, if the flux linked with the coil changes, then an EMF is developed, and the magnitude of EMF developed is directly proportional to the rate of change of magnetic flux. Then another one is Lenz's law is there. Lenz's law. So Lenz's law states that both are opposite. Similarly, we can directly write E equal to minus d phi v by dt. So electric field is written as capital E and EMF is written as curl E. So this is Faraday's laws of electromagnetic induction. And another formula or another theorem is Ampere's circuital law. So Ampere's circuital law is line integral of magnetic field B dot dl. Line integral over any C, you can write down C or L. C is closed circuit, that is said to be contour, or normally you can write down length. Line integral of magnetic field over any closed path. If it is closed circuit, then its line integral must be equal to mu naught times the total current flowing through it. This is Ampere circuital law. Here you can see this is line integral. Here you can see it is surface integral. If integration is taken over surface or area, that is said to be surface integral. Either it is written over S or it is just given two integrations. Two means two dimension. Two dimension means plane. Plane means area. If it is three integrational symbols, then that is volume, and single integration means that is line, or double integration means surface, triple integration means that is volume. Clear? All these laws are the basic fundamental laws of electromagnetism or electromagnetic theory. Whether you remember what is mu naught or not? Mu naught, magnetic permeability of free space. Similarly, epsilon naught is permittivity of free space. Next we have displacement current. This Ampere circuital law, which states that the line integral of magnetic field equal to mu naught I. There is some modification, and this modification is done by Maxwell. So this modified law is also said to be modified Ampere circuital law, which is done by Maxwell. So what is displacement current? We'll see now. We consider a source, AC source is there in a circuit, and a capacitor is used here. Capacitor. AC source means some amount of current is flowing through the circuit. AC source is there. So here current is flowing. We consider two closed circuits. This is C2, another one is here C1. C1 stands for closed path 1, C2 stands for closed path 2. Now we are going to apply Ampere circuital law, because Ampere circuital law, you know that B dot dl equal to mu naught times the total current flowing through it over the closed path. For fast surface, we can write down C1. C1 is for closed path 1, and magnetic field is written, let B1. So B1 dot dl equal to mu naught I, because the amount of current flowing through the circuit is I. Again, if we apply for C2, this is integration over C2 B2 dot dl. According to Ampere's law, line integral of magnetic field must be equal to mu naught times the total current flowing through it. So how much of current is there in the space here? How much of current? There is no current, because from the definition of parallel plate capacitor, you know that the parallel plate capacitor consists of two plates parallel to each other, having equal area separated by a space. That space is either empty or filled with any dielectric medium. If it is empty, there is no connection, so there is no charge and there is no current. If any dielectric medium is there, then still there is no current. If there is no current, then right hand side will be 0. Give it equation number 1, equation number 2. Again I am repeating, we have taken a circuit where AC source is there, which gives I amount of current, and a capacitor is connected in the circuit. To apply Ampere circuital law, we use two closed paths, one over the circuit, one between the two plates of the capacitor. For circuit, we get B dot dl equal to mu naught I formula. Here we get B dot dl equal to 0, because there is no current. But if there is no current, then how current is transferred to the other part? Because you must have known that capacitors are used in fan. If one side current is entering and in between there is no current, then how current is traveling to the other part? That is the question. So Maxwell modified this contradiction, because if you see from Biot-Savart law, you know that magnetic field is directly proportional to current. So whatever the magnetic field present on the circuit must be same. So LHS of equation 1 must be equal to LHS of equation 2, because B1 equal to B2. B1 equal to B2 because same amount of current is flowing through the circuit. If B1 equal to B2, then mu naught I must be equal to 0. That is mu naught I equal to 0. Mu naught is not 0, that means I equal to 0. If I equal to 0, this is wrong, because the AC source is there. That means some amount of current is flowing through the circuit. That means whatever we assume that there is no current in between the two plates. That assumption is wrong. So Maxwell modified this theorem by introducing displacement current. Then what is displacement current? So he modified and write the formula like this. The modified form is B dot dl equal to mu naught I plus id. Where I is the conventional current and id is displacement current. Then let's discuss about what is the formula for displacement current. You must have known the Gauss theorem. Already we discussed. According to Gauss theorem, flux equal to Q by epsilon naught. So Q equal to epsilon naught into flux. From here, displacement current arises. That means from flux. Whenever the space between the parallel plates is empty or filled with any dielectric medium, there is a change in flux, there is a change in electric field. Due to that, there is an arising or development of another type of current which is to be displacement current. So displacement current is equal to epsilon naught d phi e by dt. d phi e by dt. What is phi? Phi is electric flux and epsilon naught permittivity of free space. Again we know that flux is dot product of electric field and area. So E dot A will be EA cos theta. If both are along same direction, cos 0 and cos 0 is 1. So area part we can take outside, that is a constant quantity, dE by dt. So we get this is the displacement current formula, epsilon naught A dE by dt, rate of change of electric field. So whenever the electric field varies, you can see dE by dt is there. Displacement current exists only when electric field vary with time. If electric field remains constant with respect to time, derivative will be 0. For that reason, over the circuit, displacement current will be 0. But in between the plates, displacement current will exist. So displacement current exists only when the electric field varies with time. So this is the formula for displacement current. I hope you understand. Still, if you face any problem, you let me know in the comment section. Okay, we'll go to the next part. That is the Poisson's and Laplace equation. So what is Poisson's equation and what is Laplace equation? These are just modified form of Gauss theorem. Okay, so Gauss law, from Gauss law we know that electric flux equal to Q by epsilon naught. Clear? Again here we can write down E dot ds integration over s equal to Q by epsilon naught. This is Gauss law in electrostatic, that is net electric flux must be equal to 1 by epsilon naught times the total charge enclosed by the surface. So if you see, if rho is the volume charge density, volume charge density means then rho equal to dq by dv. So q equal to, can I do dq equal to rho dv, can I do, or q equal to, can I do integration over v rho dv. This is the formula for volume charge density. If we have taken surface charge density, this is sigma ds. Line charge density, lambda dl. Volume charge density we have taken q equal to rho dv. We can use that in equation 1. So if we use, we will get on left hand side we will have E dot ds integration over s equal to, on right hand side we will have epsilon naught 1 by epsilon naught and integration over v rho dv, equation number 2. Now you can see on equation 2 we have on LHS surface integral, on RHS we have volume integral. So here that Gauss divergence theorem, Stokes theorem still comes into play, where we have to convert from one type of integration to other type. Because we cannot equate, because on left hand side we have surface, on right hand side we have volume. Either we have to convert both into surface integral, or we have to convert both sides to volume integral. Then we can equate, or then we can calculate. So if we use Gauss divergence theorem, to LHS, of equation 2, LHS is here E dot ds. According to Gauss divergence theorem, E dot ds equal to, or A dot ds equal to div A dv. So E dot ds equal to div E dv. So we can write down div means del dot E dv. Clear? Del dot E dv. Now we converted it. We have to use this value in equation 2. Clear up to this? E dot del dot E. Otherwise you can see the Gauss divergence theorem we are using here. So we can use that here. So in next page we will have del dot E dv. Integration over v equal to 1 by epsilon naught integration of rho dv. Again we can see both sides. Integration over v, we can write down del dot E minus, if we take to left hand side, equal to rho by epsilon naught dv equal to 0. If integration of a quantity is 0, the only possibility is that quantity is 0, because there is integration of everything, we will get some value except 0. But if it is derivative, then derivative of a constant 0, but integration of a constant quantity is not 0. So integration of this term is 0 means only possibility is that this term is 0. So del dot E equal to, or del dot D minus rho by epsilon naught equal to 0, or you can write down del dot E equal to rho by epsilon naught. Vector here you can give, vector here also you can give. This is the relation between E and rho. Again we have the relation E equal to minus grad V, negative gradient of potential, the relation between electric field intensity and potential, we can use that here. So del dot del V minus equal to rho by epsilon naught, or dot product of any vector with itself is always equal to square. So del square V negative equal to rho by epsilon naught, or del square V equal to minus rho by epsilon naught. This is Poisson's equation. Okay, this is Poisson's equation. This is Poisson's equation. Del square V equal to rho minus rho by epsilon naught, or del dot E equal to rho by epsilon naught. Now what is Laplace equation again? Because we have given heading Poisson's as well as Laplace equation. From here you can find out what is Laplace equation. In a charged free area, for example free space. Free space means there is no charge. Charged free area Q0. If Q0, then rho is nothing but amount of charge per unit volume. If Q0, then rho is 0. If rho 0, then this equation will be del square V equal to 0. So this is Laplace, nothing else. This is Laplace equation. Clear? This is all about Poisson's and Laplace equation. Practice all these derivations by writing. Okay, and still if you face any problem, let me know. in the comment section. In next video, we will discuss about all the Maxwell's equations and their derivations. Okay, thank you.